Greetings everyone, my name is Tom Irvine and this is the NASA Engineering and Safety Center NESC Shock and Vibration Training Program, and this is the very first unit of this training program. I'd like to start by thanking Dr. Curtis Larson for making this effort possible, and Dr. Larson is the NASA Technical Fellows for Loads and Dynamics, and he is the head of the NASA Engineering and Safety Center NESC Loads and Dynamics Technical Discipline Team, TDT. So thank you to Dr. Larson. So the NASA Engineering and Safety Center is an independent funded program with a dedicated team of technical experts, and it was formed in 2003 in response to the Space Shuttle Columbia accident investigation. NESC's fundamental purpose is to provide objective engineering and safety assessments of critical high-reach NASA projects to ensure safety and mission success. And there's also a NASA Engineering and Safety Center Academy, which is an educational outreach effort, and these presentations are part of that outreach. And if you go back and read the National Aeronautic and Space Act of 1958, which was the charter for NASA, part of NASA's role is to provide expertise and research and development on behalf of the U.S. space community, both government-related and commercial space, as well as U.S. military. So part of the role then is to provide research and educational opportunities and assistance to military and government agencies and commercial space. So some of the services that NESC offers are to provide a second pair of eyes. For example, we can help perform design and analysis reviews or test support, flight accelerometer data analysis, provide tutorial papers, perform research as needed, for example, to develop new methodologies or software, and also, as I mentioned, to provide an educational outreach via the NESC Academy. So there's a web link there that you can go to find more about the educational offerings. And you might ask, you might be curious about the funding. NESC already has funding available, so as government agencies or the U.S. military or even commercial space needs support, in most cases that could already be covered. So we're going to have a presentation here, and this is actually being not live. This is being recorded separately, but you're welcome to sit in on the webinar live presentations, which will be recorded in the future. And you're also welcome to contact me via email at tom@vibrationdata.com. And if you have any questions or need any assistance, I would be happy to help you with that. And also, I would highly encourage you to visit the Vibration Data blog. This is http://vibrationdata.wordpress.com. And many of the materials that we are going to be covering in this class, for example, MATLAB scripts and data samples and the basic PowerPoint slides, are available on this blog. And some of you have already been there before, but I'll just show you what it looks like. So here we have the Vibration Data blog, and if you go to the search box and put in Vibration Data Signal Analysis, then click on the search, then click on Vibration Data MATLAB Signal Analysis Package, and this will lead you to a zip file. Now, many of the functions, not all, but many of the functions that we are going to be performing in this series of units are available within this vibrationdata.zip signal package. And this is a MATLAB GUI, graphics user interface, multifunction signal analysis package. And the main script is vibrationdata.m, and there are numerous supporting scripts. And this is something that I'm it's a continual work in progress, so if you have any things you'd like to see added to this software package, please send me an email, or you can contact me via phone as well. But please download this file and extract it. And if you're going to be using this, you're welcome to use it for your work problems. But if you are going to use it, you probably need to check back periodically because, again, I'm adding additional features, and occasionally I'll find a glitch or something, or a bug that needs to be fixed. So let's go back to our slide presentation here. And we're going to start off with some very simple material. Now, this is much of the material that we're going to be covering is something that you may have learned already in your high school class, for example. But it's just a good idea to review, and we may have some of our students here who maybe never had a formal vibration class in college. So let's just go ahead and get started with this. And we're going to start off with this is actually a sound pressure time history. Now the y-axis is uncalibrated sound pressure, and the x-axis is time in seconds. And this happens to be some data recorded from a tuning fork. And the tuning fork has an A note, for those of you that are maybe have had piano lessons or musicians. Now, as we go along in this class, we're going to learn some very sophisticated tools for frequency analysis and resolution. We're going to be learning Fourier transforms and fast Fourier transforms and waterfall FFTs and time domain curve fitting techniques, and those are all very useful, and they all have their place. But for something that's nearly pure sinusoidal in a textbook sense, just counting the peaks and dividing by the duration is probably as accurate as any other method. And it makes it easy to understand conceptually what frequency is. So this happens to be a time segment. It starts at 0 seconds and it goes to 1/10 of a second. Now if we go along and count the number of positive peaks, and I'm not going to actually do that, but I'll just tell you there are 44 positive peaks there. Well, if we divide by the duration, 0.1 seconds, we get 440 peaks per second, and positive peaks per second, or you could say cycles per second. And the way we like to use the unit here is 440 hertz. So that's the frequency of this tuning fork. It's natural frequency. It's also the first natural frequency, so it's a fundamental frequency. Now I've got a few little interesting things here that we can take a look at. So if I can maneuver to the correct file here, if you'll bear with me for a moment while I get to the correct file. Okay, so if we go to the webinar Unit 1, that's on my local hard drive, so you don't need to remember that path. And we go to Tuning Fork Mode 1. So this is just it's from a finite element model that I made years ago. And I click on this AV file. I need to pull it over here. Let's start that over here. So this is the fundamental natural frequency of a tuning fork, and you can see that the two forks, or arms, or you might call them tines to be more precise, those are vibrating 180 degrees out of phase with one another. And that's predominantly the mode that gets excited when the tuning fork is struck with an impact or by some other method. Now you may have experience with tuning forks if you're a musician, for example, or sometimes doctors will use these for hearing tests or even for nerve conduction tests as well. Then the second mode is kind of interesting. There's sort of some torsional or twisting action going on, but then there's also bending action of these tines as well. Now this tuning fork mode, it's more difficult to excite, and you probably would not to hear it very clearly, if at all, if you excited the tuning fork in a typical manner. Now here's the third natural frequency of the tuning fork. So we have some, I'll call it some in-plane bending going on. And the third mode would also be difficult to excite, but I guess if you worked at it, yeah, you could excite it. So what else can we do with this tuning fork data here? Well, I've got a program I'll show you. It's kind of a fun little program to run. And I'm going to open up my MATLAB here. Now, I've got a program here, and what we're going to do actually is we're going to take a textbook sine function, and we're going to do a numerical curve fit to this data. And the way this will work is the textbook sine function is going to have amplitude, it's going to have phase, and it's going to have frequency. And we're going to take those three parameters, and we are going to vary those three parameters randomly. And we're going to come up with maybe several thousand trial sine functions, and we're going to compare each trial functions to the raw data. And the way we do that is we're going to take the trial function and subtract it from the raw data, and the idea is to minimize the residual error. So we want to come up with the best curve fit through mostly brute force random number generation, but then I also do have some built-in convergence routines built in. So if we go to our vibration data, our MATLAB workspace here, or command window I should say, and I have a program, and this is available on my blog, and it is called SineFind. So SineFind. It's available on my blog. You can freely download it. So I'm going to say enter, and I'm going to say, well, what does this program do? This script do? This program performs a sine curve fit for an input file. The time history must be in a two-column matrix format, time in seconds and amplitude. So I'm going to do choice number 1, which is an external ASCII file. So I'm going to call up a file, and it's called tuning_fork.txt. This is some measured acoustic data, sound pressure data. It's uncalibrated, so we don't know how many psi or decibels it is, but that's okay for what we're doing here. And actually, the typical way to excite a tuning fork is to, well, if you had it in your right hand, you could take it and you could just wrap it against the hard part of your left palm, for example. And that's something that, say, a doctor would do if you were trying to check your hearing or your nerve conduction. Sometimes these tuning forks are also mounted in wooden boxes, and there'll be a little wooden mallet with a rubber tip that you can tap against the sides of the fork. Some people might think, well, it's a steel tuning fork, why don't you just take it in your hand and strike it against some hard surface? And yes, you can do that, no work, but you might sort of damage or cause some cracks or nick in your tuning fork, so that's not recommended. But any of those ways that I mentioned will excite the tuning fork into a transient response, and the damping or decay will be very slight, but in this case we're just looking at a half-second worth of time, and there is no decay going on. Well, the tuning fork still has damping, but I'm actually exciting it into a steady state vibration. And how am I doing that? Well, I'm using a technique called magnetostriction, and we'll talk about magnetostriction in an upcoming unit. But let's go back to our SineFind program, and we're not going to try and curve fit the whole half second. Maybe we'll just take 1/10 of a second or so, or maybe 2/10 of a second. So let's start the segment time at 0.1 seconds. The ending time will be 0.3. The number of trials per frequency, I'll do 5,000. We're only going to be searching for one frequency. Later on, when we run SineFind, we'll be looking at signals that have a beat frequency effect or multiple sinusoids, but in this case we just have one. There's two strategies we can use. We can manually enter a frequency, which is the estimate, estimated frequency, or we can let the program automatically figure out what the frequency should be. So let's do choice number 2. This will be an automatic. Now you can see real time what's going on with the curve fit in our progress, and there's some numbers scrolling by, and this 442.7, that's an estimate of what the natural frequency is. Okay, so 442.4 hertz, and phase angle is not important for this case. So it looks like we got a pretty good curve fit here. Let's sort of zoom in a bit, if I can figure out how to work the zoom. Nope. So then what I need to do is go to reset view. Let me try and zoom in again. Well, you get the idea. We did a really good curve fit. So this gives us confidence that 442.4 hertz is the natural frequency of the tuning fork. And we already did the count the peak method, and we estimated 440 hertz. So this maybe gives us a better, a more finer, or more precise, or more accurate estimate of what that frequency is. Now I've got a couple of 2 or 3 things else I want to show you about this tuning fork. And one is if we go to vibration data blog, and if we type in piano on the blog, in the search box, and we can go to some music acoustics here. So I'm going to click on that, and I've got a diagram here, and this shows the piano keys. And if we download this as a PDF instead of opening it up in the web browser, you'd see this is a little more neat and tidy in terms of the way the keys are presented. In fact, let me just go ahead and do a save link as, and go to that file here, if you'll bear with me. Oops. Try this one more time. Excuse me, so if we're going to go to C, MATLAB. Okay, that's where I put it. Okay, I've got a few too many directories and things going on my desktop, so you'll just have to be patient with me. Okay, this is a better look of what you'll actually see. So it's interesting to look at a piano keyboard, and if you take piano lessons, you'll learn that middle C is 261.63 hertz. Now, our case, our tuning fork was an A note, and more precisely, according to some terminology, it would be an A4 note. And there you can see it's 440 hertz. Well, you might ask then, why does our experimental data show that it's 442 point some odd hertz? Well, due to manufacturing, tolerances, and there's a little bit of a deviation there from the ideal. But for music purposes, 442 hertz is close enough to 440 hertz, so we're not going to worry about the 2 hertz difference there. Now, if we go 1 octave lower, that would be 1/2 the frequency. So you can see there's an A3 note at 220 hertz. And if we count both the white keys and the black keys, there are 12 steps from A3 to A4. And another way of saying that is the keys on the piano, both white and black together, have a 1/12 octave spacing. So we're going to be talking more about octaves as we go along in this series of webinar units, but that's just sort of a brief introduction. So we click out of that, click out of this. So we just looked at the music acoustic page on the vibration data blog. And I'm going to go to, while we're on the blog, I'm going to show you something else. Let's go to, let's see, what do we have here? There's something called a Rice characteristic frequency. Now, if we take let's take the signal y. So we have some amplitude y from a time history. We take the standard deviation and we deposit it there in the denominator. Now in the numerator, we're going to take the standard deviation of the first time derivative of the amplitude. So, for example, if y were displacement, then this would be velocity in the numerator. Or we could have, if y were velocity, this would be acceleration in the numerator. And this also works if y is pressure, like sound pressure, as well. Then we'd have the time derivative of sound pressure. But anyways, if we divide these two standard deviations and divide by 2 pi, that's an estimate of the characteristic frequency. Now this formula is exact. It's exactly precise if we have a pure sine wave. Now the tuning fork data was close to being a pure sine wave, but there was a little bit of amplitude modulation going on as well, so it wasn't a perfect sine function. But let's see what happens if we try and calculate the Rice characteristic frequency for the tuning fork. So how do we do that? So let's go to remember I told you about the vibration data script, vibrationdata.m, and you can download this from the blog. So this has all sorts of functions, and throughout the course we'll be going through some of these functions. So the first one I want to take a look at is a time history and its statistics. So I'm going to begin the signal analysis, and this will be an external ASCII text file, and it's tuning_fork.txt. The y-axis, I'm just going to say unscaled sound pressure. We'll also be taking a look at the histogram, more about that later. So then I just enter in the file name. We've already selected the file via the pop-up window, y-axis, click on calculate, and the histograms, we'll cover those a little bit in a minute or two. There's our basic time history again. You've seen that before. It's from the tuning fork. But let's go over to this box here. So the result box here has some information. It has some information on the time step delta t, and sometimes we'll get data that has a variable time step. So this will also show the minimum time step dt min and the maximum time step dt max. We also have the sample rates. The sample rate is the inverse of the time step, and then SR minimum, the minimum sample rate, is the inverse of the maximum delta t, and then the maximum sample rate is the inverse of the minimum delta t. So this just gives us an idea of whether or not the delta t time step is constant or not. We have some statistics here. We have the mean value. For our purposes, the mean value is essentially 0. Then we have our standard deviation, our RMS. Well, what's the difference between a standard deviation and an RMS? Well, we tend to use those terms kind of interchangeably in vibration analysis. But I want to show you an important formula here. So if we have a signal, maybe I'll put this at a bolder font or larger font. RMS squared equals the standard deviation squared plus the mean squared. So the RMS value is always greater than or equal to the standard deviation. And RMS, as most of you would know, is root mean squared. So it's always greater than or equal to the standard deviation. And sometimes we'll represent a standard deviation by the Greek letter sigma, or we might say 1 sigma for one standard deviation. And then we have the mean. Well, in many cases, not all, but in many cases with measured dynamic data, either through AC coupling or high-pass filtering or just the nature of what we're measuring itself, in many cases mean will be 0. Not always, but in most cases probably mean will be 0. Well, if mean 0, RMS and standard deviation are the same numerical value. That's pretty much what happens here to 4 decimal places for our tuning fork data. So we get a little lazy, a little sloppy, I guess, and we kind of use standard deviation and RMS interchangeably. But please know that they are actually different quantities. Okay, enough about that. Kurtosis, we'll be covering that later on, but for a pure sine function, kurtosis is 1.5. When we get to broadband random vibration, then we're going to find that if that vibration has a normal distribution, then the kurtosis will be 3.0. Then we see the maximum and minimum. Now crest factor, that's sometimes an important parameter. That is going to be a ratio of the peak absolute value divided by the standard deviation. So this just gives us an idea of what is the scale factor to go from the standard deviation to the highest absolute peak. And then I was talking a few minutes ago about the Rice characteristic frequency. In this case it is 445.3 hertz. So that's just another way of estimating the natural frequency. But of the three methods we've looked at so far, the most accurate in this case in terms of getting fine accuracy, I would say was the sine-fine curve fit. Okay, so that's pretty, oh, one other thing too. A lot of times when we have signals, we like to take a look at the histogram. Well, how do you calculate a histogram? Well, we're going to take the amplitudes and divide them into bins. So we'll have a number of, typically these would be evenly spaced bins. Now this is digital data, so what are we going to do? We're going to count the points of the instantaneous values that fall within each amplitude bin. And we're going to plot that up, and it's going to be a histogram. So here's the histogram of the tuning fork data. So the y-axis is counts, that's the number of data points, instantaneous data points within each bin. Then the x-axis here is unscaled sound pressure. Now a pure sine function, now our tuning fork isn't quite a pure sine function, although it's somewhat close. A pure sine function has a histogram that's called by the nickname bathtub curve. And the explanation for this bathtub curve is that the sine function likes to dwell at its peak negative level, its peak negative peak level, or its peak positive level, with a somewhat rapid transition in between. So that's the nature of a pure sine vibration. Now, later on we're going to be talking about white noise and broadband random vibration. And if we have a random vibration that has a random vibration would typically have a bell curve histogram, or you might say a normal distribution, or you might say a Gaussian distribution. So Gaussian distribution, normal distribution, bell curve distribution, those we kind of use those terms to describe the same thing. And we'll be talking more about random vibration in an upcoming unit. There's also one called the absolute peak value distribution, and we'll be talking about that later, so I'm not going to cover that now. So anyways, it's very typical when we get vibration data that we have a task of trying to figure out what the parameters are, do some signal identification. If we have a sine function that's present in our data, we have to think, is that an excitation function? Is it a natural frequency? Is it a natural frequency being excited into resonance, or what is it? What's going on? So part of what we need to do is to develop some critical thinking skills. That's one of the themes in this course. I want the students to be able to develop some critical thinking skills. Well, let's move on to some other slides here. So we're talking about natural frequencies, and there's different ways to demonstrate this, and we'll show one in a minute. But a natural frequency is the frequency at which a mass will vibrate if it is given an initial displacement and then released so that it may vibrate freely. And free vibration is also called simple harmonic motion. And an object has both mass and stiffness. So the engineering structures, whether they're plates or shells or circuit boards or or launch vehicles, whatever they might be, they both have both mass and stiffness properties, and we're going to be talking about those. So the spring stiffness will try and snap the object back to its rest position if the object is given an initial displacement. The inertial effect of the mass, however, will not allow the object to stop immediately back at the rest position, so the object is going to overshoot its mark. So the mass and stiffness forces balance out to provide the natural frequency. You can also think of this in terms of an exchange of the kinetic energy from the mass and the potential energy from the stiffness. And the one energy gets entirely converted into the other form of energy, and that energy conversion takes place at the natural frequency. And I've got a video here. Let's see if I can find this video. And this is a slinky, and I'm holding it upside down. And I'm going to give the slinky an initial displacement. Now, after I release it, the stiffness property from Hooke's law will try and pull the slinky back to its equilibrium or rest position. But the slinky is going to overshoot the rest position mark due to its mass or inertia. So what I'm explaining in this video is that we're going to give the slinky an initial displacement there, and then we're going to watch it in its free vibration. And that's going to occur at the natural frequency of the slinky. So here I am, I'm releasing the slinky, and it's going through a couple of cycles of oscillation, each time overshooting the rest position. Now eventually it does return to the rest position after a number of cycles oscillating its natural frequency. So eventually the slinky returns to its rest position after a number of oscillations. There is a property called damping going on, and damping is it's an energy dissipation mechanism, and that occurs because there's frictional effects in the coil. There may be some air resistance, for example, and some boundary damping. But anyways, what I've done there is to sort of demonstrate natural frequency with the slinky. So let's see what we can do with the slinky. Let me give it an initial displacement again. So now I'm giving it an initial displacement, and I'm going to do a little trick here. And if you watch the top of my hand, the top of my hand is actually vibrating at the natural frequency of the slinky. I'm exciting this to its natural frequency, which is called resonance. So this is a resonant effect. Motion going on with my hand, and there's dynamic amplification effect. Just barely see. And I would call this a base excitation effect, even though my hand's at the top of the slinky. Or you might call it a seismic excitation or support motion. Amplification factor occurring. So you might want to just get the slinky of your own, buy it at a toy store or something, and play around. It's a good way to identify natural frequencies, or demonstrate, I should say, natural frequencies. Okay, enough about that. Let's go back to the slides here, and I'll show you some fun things. So we've talked about natural frequencies just a little bit. Damping. There's all manners of different damping. This is an energy dissipation that occurs, and if we give our object an initial displacement or initial velocity, the vibrations will eventually decay due to the damping property. These could be due to viscous sources, dry friction, aerodynamic drag, acoustic radiation, air pumping or sliding in joints, boundary damping, and many other ways as well. And damping is very important. We'll be talking about it throughout these series of webinar units. So when we're dealing with systems, we like to idealize them as single degree of freedom systems. And this is a system that has only one natural frequency. And even if we have a real complex structure, just to get an initial estimate of its response or to initially characterize it, we try and simplify it to be a spring mass system. But in reality, all systems are multi-degree of freedom systems. They have multiple natural frequencies. And if you want to be even more rigorous in our terminology and definitions, we might say, well, in reality, every system is a continuous system, and it has many natural frequencies. So it's kind of fun to just take a moment and think about some things we're familiar with. So here's Mother Earth, and the Earth experiences seismic vibration, and seismologists have determined that the fundamental frequency of the Earth is 309.286 microhertz. Now that natural frequency is so small, it's probably more convenient to represent the frequency in terms of its period. So the way we take the period is we simply take the inverse or the reciprocal of the frequency in hertz. So that works out to be approximately a 54-minute period for the fundamental mode of the Earth. And I wish I had a plot of the mode shape, so someday I'll need to figure out how to get one of those. But this information comes from an authoritative seismology textbook. So that is a very, very low natural frequency. Now here's something interesting. It's the Golden Gate Bridge. So the Golden Gate Bridge, it's a steel suspension bridge. It's almost 9,000 feet long. And let's think about this bridge. What type of dynamic environments do we need to design a bridge of this class to withstand? Well, obviously it needs to withstand the weight of the automobiles or semi-trailers or whatever vehicles are passing over it. That's quite obvious. But then it also has to understand potential earthquakes, because in San Francisco there's the San Andreas Fault, and there's the Hayward Fault, and many other smaller faults that sort of crisscross the coastal areas of California. And also there's the possibility of winds, and then the incoming and outgoing ocean currents as well. So let's see, talked about those already. The Golden Gate Bridge has performed well in all earthquakes to date, including the 1989 Loma Prieta earthquake. Several phases of seismic retrofitting have been performed since the initial construction. Now here's something interesting. The current Caltrans, that's the California Department of Transportation, the current Caltrans standards require bridges to withstand an equivalent static earthquake force of 2 Gs. And later on we're going to be talking about, in a series of webinars, when we get to our shock unit, we'll be talking about earthquakes and seismic forces. And we're going to actually come up with a plausible story as to how that 2G limit was derived. Now, some of you may come from the aerospace industry where you work on launch vehicles, and some of you might have to design and test avionics boxes to withstand shock events from pyrotechnic stage separation events, for example. So in some cases, those avionics have to withstand 10,000 Gs acceleration. So you might ask, well, an avionics box has to withstand 10,000 Gs, but this bridge upon which human lives depend only has to withstand 2 Gs. And well, there are some differences there. The pyrotechnic shock event happens in a matter of milliseconds, and it's dominated by high frequency energy above 1,000 hertz. But with earthquake events, most of the energy is below, I'll say below 10 hertz, and the durations are a lot longer. So there's sort of an interesting trade-off, but when we think about amplitudes and frequency content and durations, and as we go along into future units, we'll be actually analyzing some earthquake data as well as some pyrotechnic shock data as well. So here's the natural frequencies of the Golden Gate Bridge, and I wish I had a diagram of the mode shapes, but maybe at least you can get kind of an idea from the just the one-word descriptions there. So the transverse mode has a period of 18.2 seconds, the vertical mode 10.9 seconds, longitudinal mode 3.81 seconds, and there's a torsional mode at 4.43 seconds. You can also look at the natural frequencies there, but since each is below 1 hertz, it's maybe more convenient to describe the modes in terms of their periods. Here's some simple things you may be familiar with, maybe from you did this in a high school physics lab experiment, as I did many years ago. So we have a pendulum here, and we have the mass m, and it's a discrete, we'll call it a discrete point mass. Then there's length L from the point mass to this pivot point here, and this is in a 1g gravity field. So for this case, the natural frequency omega sub n for this pendulum would be the square root of g over L, where g is gravity and L is that length. Now as we do this calculation, we get radians per time as our unit, and typically it would be radians per second. And if we want to get frequency in hertz, then we would take that omega sub n and divide by 2 pi. Now this diagram is very important because over and over again in this webinar unit, we're going to be talking about spring mass systems, single degree of freedom systems, and this will be the main system that we refer to. So here we have a mass m, we have the spring stiffness k, that comes from Hooke's law. Then we have a damper or dashpot represented by its viscous damping coefficient. So for the spring mass system here, we have omega sub n is equal to the square root of k, the stiffness, divided by the mass m. And again, this would typically give us radians per second, so we would need to divide by 2 pi to convert to frequency in hertz. And even though this is the formula for the spring mass system, even if we're talking about plates or beams or shells or annular plates or some complex equipment with different structures mounted together, conceptually, in some sense, this same formula holds in that if we increase the stiffness of our system or structure, the natural frequency will go up. If we increase the mass of our system, the natural frequency will go down, and that's when I say that, it's with the square root over those terms. So I guess for complex structures, we might just take that equal sign and replace it by a proportional sign. It's just some things you might have come across. Here's a formula for the cantilever beam with an end mass, and later on I'm going to be showing you a paper that drives formulas for different beam configurations. But some of you may have seen formulas like this before, maybe a handbook or something. More about beams later on. Circuit boards. I've dealt a lot with avionics boxes in my previous career. So I just took a sample of avionics boxes where I had the opportunity to measure the fundamental frequency. And the acronyms are important, but just for this sample of 6 boxes, the lowest natural frequency or fundamental frequency was 65 hertz. Then the highest was up at 580 hertz. So the average was 328 hertz with a rather high standard deviation of 203 hertz. And the CEP was actually an older avionics box, probably from the 1970s era maybe, and it had some very thick circuit boards with very large dimensions and had the lowest net fundamental frequency. But nowadays, with increased miniaturization and surface-mounted parts being used, circuit boards get smaller and smaller, so the fundamental frequencies tend to get larger, at least for the avionics flown on launch vehicles. I think we talked about these formulas already. So if we have a frequency in hertz, Fn, we can multiply by 2 pi to get the radians per second, and then so on. And the period of oscillation is 1 over the natural frequency in hertz. We've talked about that already. A textbook I'd highly recommend that you get if you don't have it already. It's called Dave S. Steinberg, Vibration Analysis for Electronic Equipment. And this is a good book. It has a lot of real practical formulas in it. And even if the only thing you ever do is analyze plates and beams and mechanical structures, this is a good book to have. He covers random vibration, shock, fatigue, stress, dynamic stress, and I highly recommend that you get this textbook. Some of the materials that we're going to be covering in this webinars are overlap what's in this textbook or kind of based on what Steinberg has done, more or less. Okay, so here we have just a simple single degree of freedom system. It's a spring mass system. And you can see the mass value there, the stiffness there. And I've calculated the natural frequency. And I've got this is all extraordinarily straightforward here. But I have a little cartoon. So that's what the spring mass system does. It just vibrates up and down. In this case, there's no damping represented. Or you could just think, even if there were damping, this would be what the first mode shape would be if we animated it. So that's a single degree of freedom system. Now we can also have a 2 degree of freedom system, and there's various ways we can have that. I covered that already. So here's a 2 degree of freedom system with its various mass and stiffness values. So what's the mode shape, the fundamental mode shape of a 2 degree of freedom system comprised of springs and masses? So the fundamental mode has both masses vibrating in phase with one another. And you can see as we go from the bottom system to the top system, a dynamic amplification effect occurs. So you could think of this, for example, as a avionics box where the top mass was the circuit board and the bottom mass was the box chassis. So that's the fundamental mode. Let's take a look at what the second mode is. And here we have the two masses. They're vibrating 180 degrees of phase, out of phase with one another. So we have out of phase vibration there. So those are the two modes of the 2 degree of freedom system. And later on we're going to be covering mode shapes of beams and plates and other types of structures. So we already took a look at the animation. And by the way, all the animation files that we're covering are posted on my blog. In fact, if you go to the blog and you go to Webinar Unit 1 Natural Frequencies, you can see some PowerPoint files there, the tuning fork. You can actually listen to the tuning fork sound file, and some other videos that we're going to be covering here shortly, or the next 2 or 3 units. Also, this audio video presentation will be available at a future NASA website, and once we get that link straightened out, I'll post a link to the audio-visual file that you're viewing and listening to now at this site. Of course, if you listen to this, you've already found it, I guess. So that's a little bit of a funny thing to me to say. Okay, we all need a little humor. Laughter is the best medicine. Okay, what next? So we're going to go back to the slides here. Now, resonant vibration and in aerospace structures, in the field I work, it's almost always a bad thing. You know, the problem with vibration is that there could be a fatigue failure, there could be yielding, ultimate stress failure, maybe buckling. Again, as I already mentioned, fatigue is a particular concern where we have repetitive accumulated stress cycles. There's also another failure mode. It's called loss of sway space or loss of clearance. So you could have a vibrating system. In other words, it might impact into some other system. So that's something we have to look at, especially if we're doing an isolated component. We have to look at what the isolator deflection will be and whether or not whether or not the springs will bottom out, for example, or there'll be some interference with something else. But every so often, it's fairly rare, but every so often we find a practical use in aerospace for resonant vibration. So let's think about an astronaut orbiting the Earth in a space station. So this astronaut here, he needs to measure his vital signs, because astronauts in orbit, they may have decreased bone mass density, or they might have other physiological changes, for example. So they need to measure their vital signs. Well, so what does the astronaut do? Go get a Walmart grade bathroom scale and take it into the space station? Well, that'd be silly. It would not work, because the astronaut is in a state of constant free fall, and the astronaut is not weightless, but rather he experiences apparent weightlessness. And our cousins in the physics world are very precise about that point. So anyways, what the astronaut did, this is actually back from the Skylab program in the mid-70s, and but the astronaut would sit in the spring-loaded chair. Now the stiffness values of that spring-loaded chair, the stiffness was already known. So the astronaut would rock back and forth, get himself into a resonant vibration, and then the natural frequency in hertz could be measured from his rocking. And from there he could use that previous formula to back out what his mass was. So when I say previous formula, so this is the formula that the astronaut could use to indirectly calculate what his mass was. So that's one of the somewhat rare examples of where vibration in aerospace is actually put to a useful purpose. I mean, there's others as well you could probably think of. But mostly resonant excitation is to be avoided. So we talked about resonance. There's different ways that resonance can occur. It can occur when we apply a force or a base excitation of some sort that coincides with the system's natural frequency. For example, we may have a bulkhead on a rocket vehicle where the avionics are mounted, and the bulkhead's natural frequency might be excited by a motor pressure oscillation, for example. And again, as I mentioned, during resonant vibration, the response may increase until a structure experiences buckling, yielding, fatigue, or some other failure mode. And the Tacoma Narrows Bridge failure is often cited as the all-time greatest classic example of resonant vibration. But strictly speaking, no, it wasn't resonant vibration. It was a case of self-excited vibration. And we'll talk more about that in an upcoming slide. So what I want to talk about now are there are 4 methods by which a structure's natural frequency may be excited. Now, for the purpose of this class, there's actually more than 4, but there's 4 main ones. So some of you have done modal testing before. That's M-O-D-A-L, modal testing. And you've taken an impulse hammer and you've excited a structure in order to measure the natural frequency, and the damping, and maybe even to characterize the mode shape or some other parameters. So if we strike something with a hammer, that's an applied force. Some of you may play baseball or softball. When the ball hits the baseball bat, that can excite the bat's natural frequencies as an applied force. We could have airflow or wind exciting a structure. That could be a tall building. It could be an aircraft wing. It could be a flagpole. Ocean waves excite offshore structure. That's an applied pressure. Rotating mass imbalance in a motor. So we get into machinery dynamics, and that rotating mass imbalance would be an applied force. Pressure oscillations in a rocket motor, that would be an applied force. Also acoustic excitation is an applied pressure. So anytime we have a structure, we have to think, how could it be excited? And it may be excited by an applied pressure or force. There's also base excitation. Some of you may live in a place where there's dirt roads, and maybe you go drive out to take a hike or go camping or do some off-road four-wheel drive, whatever. You may encounter washboard roads, and those apply a base excitation to the vehicle. The classic base excitation is an earthquake, or some type of seismic excitation. We may have a machine tool or optical microscope that's excited by floor excitation. So some of you that may work in the semiconductor industry or at semiconductor fabs may come across that. Shaker table testing, we oftentimes take avionics boxes, mount them on shaker tables, and we apply a base excitation. Or you might call it a seismic excitation, or you might call it a support motion. So that's the second category. And one of the reasons we need to know these different categories is because that will determine our equation of motions and how we actually do our analysis. And it can also affect how we do our testing as well. Now the third one is self-excited instability. This is the most exotic of the 4. And an example of this would be airfoil or bridge flutter. And this self-excited instability, sometimes it's also called negative damping as well. Then there's initial displacement or velocity, and I already demonstrated this via the slinky. Another example is plucking a guitar string. Pegasus drop transit, we'll talk about that maybe in the next unit. Or when we accidentally drop something on the floor, well, that's actually a very complex dynamic problem, but we would say that as the object is striking the floor, it experiences an initial velocity as it impacts the floor, and we would model the system accordingly. Well, in reality, when you drop something on the floor, it's probably going to experience some plastic deformation, and which is beyond the scope of our simple linear single degree of freedom models. But nonetheless, just as a first cut, we modeled the accidental drop as an initial velocity of a single degree of freedom system. Obviously, the other excitation methods, we'll talk about magnetostriction coming up in a future unit, and you can probably think of a few others as well. But these four here will probably cover 99% of what we actually encounter in our engineering tasks that we have to perform. And we're partway through the first unit now. I'm going to go ahead and end this presentation because I like to keep these just below an hour. And when we come back in our next unit, we're going to continue natural frequency analysis and talk about different systems. So thank you for attending, and please check out the blog site. Thank you. Goodbye.